In this video, we will be talking about work and energy. The formula for work is known to be equal to FD. So W is equal to FD. Unit for work is in joules, or abbreviated as J, capital J. The unit for force is in newtons, or capital N. For distance, of course, it's in meters. So all of these units, they are SI units for their corresponding categories. So work, joules, force, newtons, distance, meters. Now, yeah, I think that's everything that you have to know for the formula. I think for work itself, it's considered a scalar quantity. But yeah, that's all I'm gonna say. Okay, let's try to solve number 1. So you slowly left a book of 2 kilograms mass. So we know that m is equal to 2 kilograms. And we have a constant velocity at a distance of 3 meters. So what's being asked is the work. Now, what do we do in this kind of scenario? We're given a mass, but here we need to look for the work. We're going to use this formula later, but for now, we do have the distance, but we need the force. Force can also be called the weight. Weight is known to be equal to mg, or yes, F or W. They can be used interchangeably, except in some circumstances. Our circumstance right now isn't one of them. So, yeah. F is equal to mg, or W is equal to mg. We have the mass, so mass is equal to 2 kilograms. Gravity is always 9.8 meters per second squared. So what is our weight? By the way, this is work. In my school, we were taught that weight and work have the same letter, which is capital W. But it may be confusing at times if you want to make sure you're not basically you want to distinguish work and weight. So perhaps for the rest of the video, I'll be writing work like the complete word instead of just W. W will just be for the weight. And yeah, that's it. 2 times 9.8, that is equal to 19.6 kilograms times meters per second squared. This entire thing, by the way, can be written as N, or newtons, since newtons is also considered kilograms times meters per second squared. So now that we have now that we have the weight, we can now look for the work. So weight and force are basically the same. So 19.6 newtons times distance of 3 meters. So as you can see here, 19.6 times 3, that's equal to 58.8. And we have Newton meters, or we can call it joules. If I remember correctly, based on what my teacher said, torque uses the unit Newton meters, and work uses the unit joules. Although theoretically they're the same, it's just that you associate Newton meters with torque and joules to work. That's just how things are for a reason. That reason I'm not really sure about. But yes, let's go with number 2. Okay, so we have a mass of 15 kilograms. 15 kilogram crate is moved around horizontal floor by a warehouse worker who's pulling on it with a rope that makes a 30-degree angle with a horizontal. Okay, so let's draw the crate first. For this kind of problem, we're supposed to draw an illustration just to be sure. So this is the surface. Uh, let's write 50 kilograms here. Free body diagram, we have our Fn, or the normal force. We have the Ff. The tension of the rope is this one. So let's just make a triangle basically. And the arrow is going that way. The angle will be here, 30 degrees. And here we have Fg, or the weight, gravitational force or the weight. And here we have, well, not exactly there. This direction is going to be our applied force, such that the tension is what? 200 newtons. So the crate slides a distance of 10 meters. So let's say this is 10 meters. The question is, how much work is done by the rope, on the crate by the rope? So what do we do in this kind of scenario? First things first, we have the mass. We have to look for the weight. Weight, which is going to be force later on, in work is equal to Fd. So 15 times 9.8, that is said to be 147 newtons. Now, with this value, since this is a free body diagram question, since we have Fn, Ff, and W in the illustration, again, what we're looking for is the work. So there is this formula. I didn't mention this earlier. Aside from W is equal to Fd, work can also be equal to F, and then we put cosine theta, and then D. So the difference only is basically we have a cosine theta in the middle, in between F and D. So when do we use this kind of formula? If we're given a scenario where a degree value is mentioned. Unlike number one, we're not given any degree value, so we use the basic formula, which is basically only Fd. So now that we have this, let's try to use it now. So work is equal to force, or the weight, which is 147. Is it? No. I'm sorry. These two are not the same in this scenario. The force here pertains to the tension. So we have 200 N, and then cosine 30 degrees, and the distance is 10 meters. So what is the work? Based on the calculator, it's said to be 1732.05081 joules. Okay, that's it for this one. What else do we have? I'm still thinking why the F here in this formula is not the same as the weight here. It was initially stated by me that work and force are basically the same. But why is it that here they're different? Yeah, that might be something that I can't answer at the moment. I do recognize my limitations. Although during the time when I was preparing for the exam related to this one, I'm pretty sure I understood everything. I didn't have this kind of question before. I wonder why I only have it now. Anyways, let's answer the next questions. Okay, so assume the coefficient of kinetic friction. So frictional coefficient, abbreviated as this symbol, is equal to 0.4. So how much work is done by the normal force? Okay, so Fn is missing, which is this one. So in this kind of scenario, since this is a free body diagram, like based on our illustration, we have something called the summation of Fy, or the summation of forces with respect to the y-axis. We have tension y, we have plus Fn, and then minus W. I think I've stated this in the previous videos. I think that was regarding uh, regarding tension. Uh, my video on tension. Um, Basically, in this scenario, Fn is positive, but in a different scenario, um, this is supposed to be minus. Perhaps if it's being pulled down instead of being pulled upwards, up, upright, coming from our perspective. Anyways, I explained it better in that video. Maybe now it's just not the time for that. Okay, so summation of Fy, it is implied in this scenario that the summation of forces with respect to the y-axis is equal to 0 newtons. There are no forces that are being applied uh, right now. Although the object is moving, possibly. Yeah, it did move since we have a distance value. So for Ty, do we have any other value? Ty is also missing. But we do have the weight value, which is this one. So this is where our weight value comes in handy. So our intention is to find Fn, but we're missing Ty. So we have to look for Ty first. There's another formula. Ty is equal to T sine theta. So tension Y is equal to T sine theta. There's another formula related to that. If you're looking for Tx, or the tension with respect to the y-axis, it's basically T, and then instead of sine, we put cosine. But yeah, that's not what we need right now. It's Ty that we're looking for. So tension is said to be 200, right? 100 newtons. Sine, what is the angle value? 30 degrees. So 200 sine 30, that is equal to 100 newtons. Perhaps I think it's time to transpose Fn to the left side. And from there, we swap the signs. Fn is going to be 47 newtons. So I suppose that is the answer for letter A. Letter B. How much work is done by the friction force? So in other words, Ff is missing. We do know this formula. F is equal to Un, or the fun formula. We can also write it as this. So Ff is equal to U, which is known to be 0.4. So 0.4 is put here. Fn is 47 newtons, right? So 0.4 times 47, our frictional force is equal to 18.8. Not sure why it's 600, negative 600 newtons. I believe that's a typo. I wasn't the one who made this worksheet, by the way, so yeah, there may be errors. So yes, we'll continue on the next video. We'll be talking about potential and kinetic energy. Yeah. But this one is all about work and energy. So yes, thanks for watching.